Let's go over a couple of practice problems for quiz 4. Starting with question 1, for this right triangle shown below, we're given that the measure of angle B is 51 degrees, so I'm going to label that in here. This is 51 degrees. And we're told that the length of side A is equal to 15. Can we solve for the remaining sides and angles? And I'll round my answers to 2 decimal places. I need to know angle A, then side B and side C. I think I'll start with the measure of angle A. The sum of the 3 angles in this triangle must add up to 180 degrees. Therefore, the measure of angle A is equal to 180 degrees, and I'll subtract off 90 and also 51. We can simply write the capital letter A for the measure of angle A. So this is really 90 minus 51, so that is 39 degrees. All right, so that's one part of this. This is 39 degrees. So we're left with side B and side C. I think we can solve for either one that we'd like to. I think I'll go with finding the length of side B. And I'm going to use angle A to help me do this. I'll just maybe right off to the side. So SOHCAHTOA, as a nice reminder for what sine, cosine, and tangent are, their definitions are. I'm going to use tangent. Tangent of this angle is the opposite over the adjacent, meaning the only thing that I won't know is what the length side B is equal to. So tangent of 39 degrees is equal to 15 divided by B. So I'll write that down next. So tangent of 39 degrees is the opposite over the adjacent, which we don't know. To solve for B, I can multiply B over here and divide tangent of 39 to the other side of this equation. This becomes B is equal to 15 divided by tangent of 39 degrees. I'm going to do this in my calculator. I'm going to make sure it is in degree mode, which it is. Great. So that's 15 divided by tangent of 39. If I round to 2 decimal places, that is 18.52. So that is the length of this side here. That was 18.52. And that leaves side C. There are a lot of ways to get the length of side C. This is a right triangle. You could use the Pythagorean theorem if you wanted to. But I'm going to go back to using one of these definitions here, and I can use either angle A or B. It doesn't matter. I think I'll use angle A, the opposite side, and the hypotenuse. The definition that will work for that is this part here, which is sine is the opposite over the hypotenuse. So I know that sine of 39 degrees is equal to the opposite divided by the hypotenuse. The process for solving this for C is going to be very similar to what we did here. That is, I'll multiply C to this side while dividing both sides by 39, sine of 39. C is equal to 15 divided by sine of 39 degrees. Again, I'm going to do this in my calculator, which is already set up in degree mode. 15 divided by sine of 39 is 23.84. And that is C. I'll even write it up here too. 23.84. So there we have it. We know all the angles of this triangle as well as the lengths of all the sides. You can say that we actually solved this triangle. In question 2, I'd like to prove this identity. The standard way to do it is to take one side and work only with that side and make it look like the other side of the equation. So you can either start with the left and make it look like the right, or start with the right and make it look like the left. I think what I'm going to do is take the left side of this equation and make it look like the right. So I'll start with this part here. So how can we even begin to simplify this side of the equation? There's not really a whole lot going on, but secant has a definition. It's defined to be 1 divided by cosine. So I'm going to take this expression and replace secant of theta with its definition. It's 1 divided by cosine of theta minus cosine of theta. So this left side here is equivalent to this. And what I used was a reciprocal identity. So maybe I'll just kind of state that off to the side here. A reciprocal identity. The term reciprocal just means move something into the denominator, make a fraction out of it. And so that's the definition of secant. All right, so again, this is the left side of the equation, slightly adjusted. I think a next logical step would be, well, I have two separate pieces. Maybe I can get a common denominator to combine this into a single fraction. So what I'll do here is, if I want a common denominator of cosine of theta, I'm going to multiply this fraction by cosine over cosine. Multiplying cosine here to the top will give us cosine squared. So this is 1 divided by cosine of theta minus cosine squared theta divided by cosine of theta. So essentially, I multiplied the top and the bottom by cosine. Now that we have a common denominator, I can subtract these two. 1 minus cosine squared theta. And that is all divided by our common denominator, cosine theta. So started here, used a reciprocal identity, combined things into a single fraction, take us down to this thing here. So what next? There's a very important identity that I'll put at the top of this slide. That is sine squared of theta plus cosine squared of theta is equal to 1. This will often show up when proving an identity. Now, it doesn't quite look like what we have here, but if you subtract cosine squared to the other side, you'll have sine of theta by itself, and on the other side you have 1 minus cosine squared theta. In fact, I'm going to write that up here. Sine squared of theta is equal to 1 minus cosine squared theta. This means I can take this and replace it with this. So I'm going to swap that in. That is sine squared of theta divided by cosine of theta. Now, what did we do going from here to here? We used a Pythagorean identity. Okay. All right, so from here, it's good to look where we're going. We want to end up with a sine times a tangent. And in the numerator, we have sine squared. If you'd like a single sine, you could rewrite sine squared as sine times sine. I think that's what I'll do. I'll say, well, all right, this is really sine of theta times sine of theta divided by cosine of theta. And how does writing this as this take me to here? Well, sine over cosine by definition is tangent, and that would leave us with sine all by itself. So maybe I'll even simplify this and write it as, well, this is really sine of theta times sine of theta over cosine of theta. I mean, certainly if you multiply these two things together, it would take you back to this step. You could make this thing its own fraction. And now I can replace this with tangent of theta. This is sine of theta times tangent of theta. If you want to be really explicit in what we did going from here to here, tangent is defined as a quotient. So you could say that we used a quotient identity. So maybe I'll just use that language down here. A quotient identity. So both tangent and cotangent are defined as quotients of sine and cosine. And that's different than secant and cosecant, which are defined as reciprocals. But anyway, we took the left side, we did a whole bunch of work to make it look at the right side, and therefore we have in fact proved this identity.